Hello. I welcome you all to this another interesting screencast. Okay, this problem is coming from the static circuit that you produced by RC Hibbeler. So we have a cross section of the beam. We've been asked to find moment of inertia of this area. Moment of inertia of an area is also called area moment of inertia. An axis that you choose to find the moment of inertia. It is used across various fields in science and engineering. If I was to give an example within engineering, I pick just one discipline, which is structural engineering. We use this for calculation of deflection of beams, for load, for buckling load calculations of column, and so many other applications. And mathematically, moment about x-axis is described as I sub x integral of y squared dA, and moment of inertia about the y-axis is I sub y equal to integral of x squared dA. Correct. Great. So these axes that will be given are passing through the centroid uh, of this cross section. This is the centroid. Okay. Alright. Before I start solving, what do you think will be the moment of inertia about this axis if we are to draw this peak to get these two axes? Okay. Alright, somewhere there. Okay, so imagine I have this axis. Let me call this as my let me wrap this part. Let me wrap this part out there and also wrap this part. Okay. Let me say this is my x prime and this is my y prime. What do you think will be my moment of inertia about the x prime? I mean, we know this, right? Right? I mean, we both know this, right? So moment of inertia about the x prime will be equal to moment of inertia about the y prime, which will be equal to what? dx divided by, and in this case, d is h, which is equal to is equal to a. Okay. Yeah. Our I sub x prime equal to I y sub y prime equal to a to the power of 4 divided by 4, right? Correct. We know about this, right? So what they did was they just flipped this square cross section of the beam so that we have it now like this. Okay, so what do you think? Do you expect us to find the same answer? This about the x-axis and the y-axis. Mind you, we just found about the x prime. Let's check it out. Okay, so again, there are a number of ways of solving this. There are a number of ways of solving this. One of the ways I'm going to assume you already know combination of a triangle. So let me pick one triangle. One triangle. So before I pick one triangle, I'll need to find this value, the value of x and the value of y there. Okay. So at that point, okay, my value of x is 0. If I plug in 0 in my equation, I plug in 0 here. What is my y? My y becomes what? It becomes a. Okay. What about my y is 0? Okay. So if I was to plug in y there in the equation, what is the value of x? X will be equal to 2. Do you agree? Correct. Of course you agree. Great. So I agree. You agree with me. Great. So therefore x So therefore, this whole length is a root of, and this also length there is a root of 2. Right. So once we know this, so in this case we are assuming that all this does not equal to 1. Like I said, there are a lot of different ways of tackling this problem. So assuming you know moment of inertia about the central axis for uh, triangle. Okay, we have this triangle whose length, this length here is equal to a root of 2, and then we have the height, which is h equal to a root of 2. Then imagine we have the centroid there. Okay, and then for the triangle, we know that the centroid is just from there is 2 over 3 h, and then this one there we just put the equal to, and this one there is just 1 over 3 of h. So imagine, okay, let's call this one as x c, and then let's have this as our x. Okay, so let's assume we know moment of inertia about the central axis for a triangle x, x sub c, sub c. So moment of inertia about the x-axis passing through the centroid. So this one is equal to 1 over 36 bh cubed. So if you know this, okay, then we can find moment of inertia of this axis in red, this one, right, about the base, right? We can use the parallel axis theorem. So moment of inertia about the x-axis will be equal to moment of inertia about the centroid axis plus the distance from the axis where we want to find moment of inertia d squared, then times the area of that particular shape. So if we were to work out this, okay, we have 1 over 36 dh cubed plus our d here is just 1 over 3 h squared, and then our area, this is our area is just 1 over bh. Okay, so if you worked out this, you expect to find 1 over 36 bh cubed. Okay, so there we have 9 times 2, which is just going to be 18 at the bottom, and then we have bh cubed. Okay, so if we are simplify this, multiply both sides by 2, then we'll find that this becomes a 3h cubed divided by 36. And then simplifying this further, there 1, there 1, this becomes h cubed divided by 4. So we know that for a triangle, the combination about just h cubed divided by 4. So if we know that, then we can work out the combination for just one triangle, and then later on multiply it by 4 about the x-axis, right? And because here you say moment of inertia about the x-axis will be equal to moment of inertia about the y-axis, because this particular cross-section is symmetrical. Is that fine? So if you found moment of inertia for just one triangle, we can multiply it by 4, right? Because each one of these triangles will have the same moment of inertia about the x-axis. You agree, right? Great. So then let's find moment of inertia now about the x-axis. Since we've known the moment of inertia, the expression which is just bh cubed divided by 4. So we said our b, in this case, our b is equal to a over root of 2, and our h is equal to a root of 2. So bh cubed divided by 2, which is equal to b, we say it is just a over root of 2. Our h is also just equal to a root of 2 to the power 3, then divided by 4. If we simplified this, then we'll have a to the power 4, right? And then here in the bottom here, root 2 to the power 3, it is just 2 root 2, okay? And then we have another root 2 that we are multiplying it, right? Then everything divided by 4. So this becomes a to the power 4 divided by 4 divided by 4, which eventually becomes a to the power 4 divided by 4 by 2 is a 48. So this is moment of inertia for one triangle, okay? And we said we have 4 of them. If the ones that I've outlined in red, we have 4 of them. So if we are to find the total moment of inertia about the x-axis, therefore we need to multiply that by 4, right? So the total moment of inertia will be equal to 4 times the moment of inertia that we found, which is going to be equal to 4 times a to the power 4 divided by 48. This therefore gives us a 4 cancels there is 1 and a 2. Therefore, moment of inertia will be equal to a squared, a to the power 4 rather, a to the power 4 divided by 4. Is that fine? So that is the total moment of inertia. This is in a case where you know the centroid or moment of inertia of a triangle. Okay, this I'm calling it as my method 1. Like I said, this problem can be attacked in different directions. So we found that our moment of inertia, our total moment of inertia, or just moment of inertia, is equal to a to the power 4 over 4. Alright, so let's work out this problem using the second method I'm calling method 2. This is in a case where you don't know the centroid of moment of inertia for a triangle. Here you don't know, you just have a problem. So what are we going to do? Okay, so what we are going to do is we'll still work with the same one triangle, find moment of inertia, the same one in red, the same one. We're going to work with it. I'll leave everything else, but we are going to integrate it. Instead, we are going to use integration. So moment of inertia about the x-axis will be equal to integral of y squared dA. So let's get a very small area again parallel to the axis of interest. Okay. So this one we just want to find for just one triangle, and its differential thickness is dy. Okay, and it's cutting our curve at x comma y. Therefore, this whole length of this small strip will be equal to x, and this height here is equal to y. Great. That is enough information for us. And therefore, our small differential area for this will be equal to the length of this strip, which is x, and then the thickness, which is y. Okay. And then we have the equation y is equal to a root of 2 minus x. Writing it in terms of x, it will be x is equal to a root of 2 minus y. Therefore, our moment of inertia about the x-axis will be equal to integral of y squared, our dA is just x dy. Okay, so we are going to be integrating from 0, okay, to this maximum point here, and integrating along the y-axis to a root of 2. Okay, so let's replace the x. Since we know what x is, let's replace this x here. We replace it here. We just want to find one moment of inertia. Moment of inertia for just one triangle, then multiply it by 4. So moment of inertia about the x-axis therefore will be equal to integration from 0 to a over root of 2 y squared, and then we have a over root of 2 minus y, right? Then dy like so. Great. So then expanding that, then we are going to have integral from 0 to a over root of 2 y squared, I mean we just say a over root of 2, then y squared, then minus y to the power 3 dy. Integrating the inside, we are going to have a over 3 root of 2 y to the power 3, right? Minus y to the power 4 divided by 4. And then we are evaluating this from 0 to a over root of 2. Great. Then we evaluate this, therefore, moment of inertia about the x-axis will be equal to a 3 root of 2. Then y there will be just equal to a over root of 2 to the power 3, then minus a over root of 2 to the power 4 times 1 over 4. Okay, so that is times 1 over 4, like that. Then moment of inertia about the x-axis, if we are to evaluate this therefore becomes equal to, the top layer is going to be n to the power 4, and the bottom we are going to have 3 root of 2, then there will have times 2 root of 2, okay, then minus a to the power 4 divided by 4 root of, sorry, a divided by 4, I mean a to the power 4 divided by 4 by 4, right? Great. So moment of inertia about the x-axis, this becomes equal to 3 by 2, that's 6, and then 6 by 2 becomes equal to 4. So a to the power 4 divided by 2 minus a to the power 4 divided by 16. If we evaluate this, moment of inertia becomes equal to a to the power 4, a to the power 4 divided by 48. So this is moment of inertia for just one triangle. So therefore the total moment of inertia will be equal to 4 times this moment of inertia for each single triangle, which is going to be equal to 4 times a to the power 4 divided by 48. And therefore this total moment of inertia will be equal to a to the power 4 divided by 4. Okay, which comes back to this same thing that we found here, right? Okay, and this is about it, and I hope the video was helpful. And if it was, thumbs up, like my video, like my channel, continue subscribing and sharing my videos. Bye bye, and see you in my next class. Check out my other video on domination.